What is this saying? Let's see if anyone can get it in 5 seconds. 1, 2, 3, 4, 5. Cannot. However, once we have our program, we can do it in less than 5. It's super fast. So we don't know what that means, but it's a message. We need to decode that. Let's find out what that is. So let's think about this one. I remember our first steps in our program was select the letter, normalize our character set to only upper or lowercase letters, and convert the letters to ASCII decimal values. So let's think about this like a computer. We want to create a function to select a letter and indicate the shift, okay? We want to normalize the letter encoding for the computer, right, the lowercase one. So we're selecting it, going to lowercase here, and convert the letters to ASCII values, right? Convert the letters to ASCII decimal values. So this is our exact algorithm, what we're going to be doing, right? So let's think about this here and let's apply it. So we have these 3 steps here. We want to do these 3 steps for the number 1 part of our Cipher program, right? Our decoding program. So we're going to create a function and to select the letter and indicate the shift. So we're going to define our variable select letter, where we have a letter and the shift amount. Okay, well, it makes perfect sense, right? We're defining a select letter variable where we're going to have a letter with a shift and shift amount as our parameters. Next, we're going to input normalize the letter encoding for the computer, where we want to convert the letters to ASCII decimal values. So here, let's say we want letter code, right? We're taking this selecting letter and we're going to create a letter code, right? So we have a variable we're creating called letter code, where we're going to take the ordinal value, right? Ordinal is going to be the decimal value of letter dot lower, so our lowercase letter. Oops, sorry. So now we know that this is going to take our letter code, whatever our letter is, and it's going to put it into a decimal value, right? The ordinal value of a lowercase letter. So it changes it all to lowercase for us, and we select the ASCII value for it. Perfect, right? Makes sense. Next steps are adjusting the transposition, right, to account for Z as the last character and A as the first character to get a new transposed letter. This is the one that we said, wow, it's a little bit more mathy, right? So in this case, we have to adjust by the transposition, define A as the first letter, define our alphabet size, and implement the transpositions, because we need to know our alphabet size, because we have to know what we divide by, right? What we get the modulus of to get the remainder function. So remember a couple of things here, right? Our base value and 26 are basically the same idea. Or no, sorry, we have a base value, which is going to be like 97 for lowercase a. And we need to know that 26 is our character length, right? Our character set. So base value is going to be like 97, and our character set is 26, right? Our character length of A to Z. So when we define A as the first letter, I'm going to put in a variable, lowercase a ASCII, right? So lowercase a and ASCII format. I'm going to make this equal to the ordinal value of a lowercase a. So lowercase a ASCII, right? Our a ASCII, lowercase a ASCII is our ordinal value of a. And our alphabet size is going to be the value 26, because we have 26 characters in the alphabet. Okay, so it makes perfect sense when we go here and say, okay, we have our lowercase a, we have our alphabet size. We're able to define our first letter, and we can define the alphabet size. So going back here, we need to make sure that we were correct on our base value, right, of 97, right, our ordinal value, and 26 as our character size. So now we have these values, right? Let's continue on, right? We have our a ASCII, ordinal of a, right? Our starting point, and our alphabet size is 26. So we know the ordinal of a is what? 97, right? So we know these values. Now we want to implement the transposition itself. So this is where our previous mathematical calculation comes into place, right? Where we said base value plus remainder of letter code minus base value plus transposition value divided by 26. So what we're going to do is we're going to call this our true letter code, right? Our actual letter that we want. And this is going to be equal to, right, lowercase a ASCII, right? So lowercase ASCII is the low ordinal value of a, which is 97. That's our base value right here, right? We could type in 97 and hard code it, but it wouldn't adjust for upper and lowercase. So we know that this is our base value plus, what is our letter code, right? Letter code minus base value, right? So we have letter code minus our base value of a ASCII, which is 97, right? Whatever our letter code is, could be like A or whatever, B, C, D, whatever, right? Letter code minus a ASCII. And we add our shift amount. right? That's how much we're going to be shifting by, right? And then we get the percent, right? The modulus, which is the remainder function of this divided by the alphabet side. So you think of this as like, this is kind of the percent sign here is like the division here, but it's only going to give you the remainder here. So in that case, at the very end, you get the remainder plus the lowercase a ASCII. So the base value plus the remainder gives you the new location or the new letter. Okay. So does that sound good to everyone? So this is probably one of the more complex parts of the program, but with the mathematical background we've got, we can totally do this. So next, last we need to get the transposed letter. So in this case, we take our decoded letter and we say equals character, right? CHR of the true letter code. So we take the true letter code and we take the character of it. So we can take the true letter code, the new letter, and adjust it back into basically ASCII or A to Z. So we can see what the new letter is. So pretty straightforward when we think about it. It takes a little time to think it through, but once you get the math behind it, it's actually very straightforward. And once we get that, we want to get a return value so that we have a return of what we actually want to have. The return is basically what's the output of doing this little program we wrote here. So 1, 2, 3, 4, 5, 6, 7 lines, about 1, 2, 3, 4, 5, 6, yeah, 7 lines of code basically allows us to transpose any letter of the alphabet. Right, so with the